So thank you very much, everyone, for joining today's webinar. And it's my pleasure to lead this discussion. And the title of today's webinar is The Need for Combustible Dust Testing and its implication on hazard assessment as well as dust hazard assessment. And my name is Emmanuel Addai, and my background, I have a bachelor in chemical engineering, master's in process safety engineering, and PhD in process safety engineering. So with my background, I am the co-founder and the CEO of Applying Process Safety. And experience-wise, I have completed several hazard assessments, including dust hazard and incident investigation. And I have actually visited almost 48 states in the United States here and been to, I think, 6 provinces in Canada, several states in Mexico. And my longest journey flight was to Pakistan, where I conducted dust hazard analysis. And also I have over 40 publications on combustible dust with a book. And also I'm also an adjunct professor at Sam Houston State University, where I instruct courses like incident investigation, industrial hygiene, fire protection, and process safety. So roughly, this is my background. And so this is going to be a discussion. It's going to be a presentation and discussion. So I'll be giving various scenarios, and so the content will start from introduction, where I'll give an overview of combustible dust hazard, the various incidents that has happened in history, and now I'll jump into the various hazard associated with combustible dust, and now the testing, DHA, and remarks. So plant process safety is young, but we are leading in the field of process safety, where we have various services, including testing. And in the testing, we have 3 different labs. We have the dust lab, we have the gas and vapor flammability testing lab, we have electrostatics lab, and also we have the reactive chemical testing lab in our facility here in our Houston office. For consulting, our consulting ranges from combustible dust, electrostatics, area classification, then it jump to the process safety management, PHAs, incident investigation, and so forth. I think more of this information can be found in our website, so I don't want to dive much into this. And also, when it comes to training, every service, consulting service and testing services that we provide, we also provide training. So we do in-house training. We also provide online training, and also we also tailored our training to meet various client needs. So let's start from the history of combustible dust. Based on my research, the first dust explosion was recorded in the 1900s, where I think it was flour dust that actually exploded. But before 1980, I think those incidents that happened were not recorded. So the Chemical Safety Board actually did a research and recorded the recent or the various incidents that actually involve combustible dust. And based on their research, they indicated that 281 incidents actually was recorded between the year 1980 to 2005. And out of it, 119 people actually died, and over 700 people actually got injured. So that means combustible dust is actually apparent and do happen in claim life. I think these numbers here are only recorded. I don't think everything was actually recorded. So we can say here, this is the ones that they know. The one unknown, the numbers could actually go high. These are typical incidents that actually claimed some lives, and I just wanted to highlight it here. You can see the first one is the CT acoustic, where 7 lives were lost. You can see the Imperial Sugar, which is very, very popular, where there was a sugar dust explosion. And you can see the list actually continues. And so forth. So I will not go dive much into it, but you can see that in each of the scenario, there was a life which was actually lost. That means the risks associated with combustible dust is actually apparent and keep actually destroying properties, getting people injured, and also claiming lives. So I just picked this data from that safety science, some of the research that he is doing. I think this is done by Chris. And I think he has been doing a good job when gathering data with regards to various incident. And you can see the table from below. You can see the United States. From year to year, you have 2017. You can see the number of dust explosion that actually occurred, the fatalities, and also the people injured. And you can see that every year, at least there is a lot of incident associated with combustible dust. If you look at the international level, you can see from only the first half of 2023, you can see dust explosion or dust fire 159, and also dust explosion, which is 32, and number of injured, you can see 71, fatalities 48, only the first half of 2023. That means this incidents actually keeps disturbing the various industry that actually handle various combustible dust. So what are the materials which are actually involved? We can see most of these incidents are associated with wood, a food product. You can see 40% of these incidents are associated with various food product and 38% associated with wood. That means the companies which are actually handling or processing food product from the first half of 2023 were actually prompt to this kind of incident. And wood industry also becoming second, and the metal industries and others and unknown. uh, so I was not able to get the data for the rest of the year in 2024. So, but you can see that this is something which is actually occurring, and drastic measures needs to be taken in order to mitigate this kind of hazard. So what are the equipment actually involved? I'm still on the first half of 2023. You can see most of these actually happens in the various storage silos. That is, it could be a bin, it could be a hopper, it could be a silo. You can see almost about 38%. And also, you can see dust collector being the second on the list. Uh, some of them are no details, so we cannot actually attribute it, but you can see dust collector and dryers are also very paramount when it comes to these kind of incidents. And for dust collector, I think this year I also investigated an incident in Houston for dust collector explosion. And normally in the dust collector, the most finest material goes there, and with various ignition source in the maybe the filters, if it's not bonded and grounded, can actually lead to electrostatic discharge or upstream ignition source and can lead to explosion in a dust collector. So according to the OSHA, they have list of various dust that they, based on research, they know is combustible. So usually there are series of steps that needs to be taken to actually understand the behavior of the material that you handle. However, this list can actually give you an overview whether the material that I'm handling is combustible or not. And these are the data, and I think you can find it from the OSHA website. So first of all, let's try to understand what is dust explosion? How does dust explosion occur? And in order to understand this, let's start from the fundamental. What is fire? And so in order for us to get a fire, we need a fuel, we need oxidant and oxygen and ignition source. For example, I love barbecue a lot. So normally, in case I want to do barbecue at home, I need to have either my propane or my methane line or maybe my charcoal, which is the fuel. I need to have oxygen or oxidant, and normally you have oxygen in the atmosphere, so automatically 21% is always available. An ignition source could be a heat or maybe a spark. Normally for propane, for barbecue, you need a spark, and that spark is able to ignite, and now you'll be ready to actually put your meat on the fire and just consume. And that is the fundamental of everything. However, when it comes to combustible dust, it goes beyond normal fire. you need to ensure that number first thing is you need to have the fuel there, which could be your dust, maybe your sugar, your flour dust, and other material that can actually combust. The second aspect here, you need to have your oxygen. If the oxidant is, it could be the oxygen in the air, and if you are not using avoidance of oxygen as what basis of safety, or maybe you are not applying inert in your system, automatically you have 21% of oxygen in the system to actually support the combustion operation. You need to also have ignition source. So the same three aspect, or the same three parameters which is needed for normal fire, needs to be there for that explosion to happen. The fourth one is you need to have what a suspension. A typical example is if I have a dust and it's on the floor, I apply heat or spark, automatically I'm going to get ignition. But is this ignition going to create any pressure? No, it's just going to burn. But what about if I suspend the material? Yes, I'm going to generate some kind of pressure, but is it confined to increase in pressure that is going to cause destruction? That is no, that is termed as flash fire. What about if I have a confinement such as maybe a baghouse, a silo, or a bin? In this situation, I have everything that actually all the condition that needs to be met for that explosion to happen. So a typical example, if you remove confinement, automatically you're going to get a flash fire. So that means even though you are going to get a combustion operation, but nothing is there to retain the energy which is being generated during the combustion operation. What about if I remove suspension? That means I'm going to get fire. The material is just going to burn, because suspension actually increases the surface area of the material, which actually help the material to ignite super fast. What about if I remove fuel? If I remove fuel from the system, automatically there's nothing to burn. If I remove oxygen, there's nothing to support the combustion operation. And if I remove ignition source, that means there's nothing to initiate the combustion. So these are the three ways in which you can actually eliminate dust explosion. So you can turn it to a flash fire when there's no confinement. You can turn it to a regular fire when there is no suspension. And if you want to remove it to avoid the explosion altogether, that means you need to remove either fuel, oxidant, or ignition source. So there's also another scenario where which is very, very problematic in the industry. And I think that will cause the total destruction of the imperial sugar, which is what dust accumulation and also secondary explosion. Secondary explosion results when there is an initial explosion. You have dust accumulation on various equipment such as surfaces, or maybe on the side of the equipment and the ceilings. And the initiation pressure from the first explosion automatically is going to shake the system, and the system is now is going to create a dense dust cloud. And since from the first explosion you already have your combustion operation, the heat automatically is going to ignite the dust cloud which is being generated from shaking of the system. You're going to have a secondary explosion. For imperial sugar, there was a first explosion on a conveyor, enclosed conveyor belt, and there was also dust accumulation all over the building. So the first ignition, actually the pressure wave actually shake the whole system, and the dust lodging on the ceiling and on other surface begin fell down. And from the initiation, from the first explosion, there was already heat to actually start the second ignition, and that was massive and caused the total destruction. So always when we are thinking about that explosion, we should not think about the initiation or the first explosion. We need to also think about the secondary explosion. So what does the standard says? We have the NFPA says 60, the section 5 of it, and also NFPA says 52, which is section 5. Always requires that anytime you handle any material, you need to determine whether the material is actually explosible or not. That is the first thing that needs to actually come to your mind. And so, first of all, you need to check, is my material explosible or not? If the material is explosible, and which we will dive more detail in the subsequent slides. So I don't want to actually squander all my time here, but I'll discuss this in more detail. So first of all, we need to know whether the material is combustible. If it is combustible, then we need to think about measures to prevent that explosion. If the material is not combustible, we need to think of fire hazard. So I have a diagram here just to follow the steps on how the tests are being generated. So let's assume I have just a powder. I don't know anything about the powder. First of all, I need to, if I know that the material is combustible, then maybe screening for explosivity, maybe you can find from SDS sheet or something like that, whether the material is combustible or not. If I don't know and I know that it's a potential to ignite, then I need to do the explosive testing or explosivity testing. If it's positive, then I'll come back to further testing. So right now you can do fire testing, we can do thermal stability, but I'm going to go into the middle here where to do the various explosion characteristics, because if the material is combustible, I need to figure out how combustible the material is. What is the ignition sensitivity? How easily can the material ignite? In case the material ignite, what is the pressure which will be released? So those are the things that have to come to my mind. And that is what every consultant, before they actually visit a site or maybe look at any operation, these are the thought that comes to the mind always. Its material is combustible. If it's combustible, how combustible the material is, what is the energy that can ignite the material, what is the minimum temperature that actually can ignite the material. What about if the material ignites in a dust cloud, what is the maximum pressure it will be released? And this is some of the things that we need to consider. And if also I have the thought of preventing the explosion, then I need to go back to the first that the dust explosion pentagon. That is something that I have to also consider. Am I able to remove the oxygen concentration? Am I able to remove the concentration below a specific element? These are some of the things that needs to be considered. So first, we consider, okay, I have a powder. The first thing that, if we don't know anything about the powder, is we do something called explosibility screening test. We call go or no go test. Go or no go test is just yes or no test. And there are three types of equipment that you can use to determine the go or no go test. You can use the 20-liter sphere. That is the standard, and that's what we have in our lab here in Applied Process Safety Lab. So we have the 20-liter sphere, and in this case, we have a dispersion cap. We disperse the dust into the chamber. We have ignition source, 10 kilojoule igniter to ignite to see whether the material is explosible or not. In order to determine whether it's explosible or not, we need to know the pressure ratio, whether the pressure ratio is actually greater than 2 or less than. If it's greater than 2, it's considered as explosive. That is the standard ASTM standard, so I can change it. Or you can use the maximum pressure, which will be released after ignition. If the material, the pressure is greater than 1, we consider material as explosible. If it is less than 1, we consider non-explosible. So this is the first test that needs to be conducted if you don't know anything about your material. What about if the material is not explosible? You test it and the pressure ratio is less than 1, or the PM is less than, and the pressure ratio is less than 2, and the PM is less than 1. Then the only thing that has to come to my mind here, now the material is not explosible. That means in the cloud form, I don't have that explosion risk. However, I might have fire risk. So we have something called burning rate test or the combustibility testing. So where we have the powder, we can see how we arranged on a train. We apply heat to it to see whether it can propagate. There are several materials out there where when you suspend the material in the air, automatically it's not going to ignite. But as soon as you apply heat, you can see it burn. Last week in the lab, we have a similar situation where we have a powder. We test the go, no go test. It was not go. It was not explosible. Then we tried to do the burning rate. We noticed that the material started decomposing. That means there was a reaction happening. So in this case, I'm not going to tell the client that the material is not actually, there's no hazard. Maybe there's no explosion hazard, but there is actually a fire hazard. So if the material is not explosible, we should not say, okay, yes, we are okay, but we need to check the combustibility behavior of the material as well. So how do I actually ensure my facility is safe? And everything is going to highlight on the testing and the application in the industry. So the first thing that needs to come to my mind here is, can I prevent the explosion? And there's a saying that prevention is better than cure. So I always need to have the mindset is, how can I prevent this explosion? And there are some tests that we need to do to confirm on how we can actually prevent this kind of explosion in the various industry. So the first thing here is I need to know the concentration. What is my minimum explosive concentration, which is the least amount of dust cloud in the air that would actually propagate flame. And I need to also know the oxygen concentration and also dilution of dust addition. If I'm having a hybrid atmosphere, I will be discussing this soon. So the first thing is to know the minimum explosive concentration. As I mentioned initially, it is the lowest dust suspension concentration that will support flame propagation. That is the most important thing there. The minimum concentration. So at that particular concentration, there's just low amount of fuel or material to combat. So normally we call it at the lean side of it. So normally the pressure ratio at this point is always low because you are the lean side of, and I'll show a diagram to explain this to you very soon. And also we also have something called upper explosive concentration and or limit. And this one normally is of no use because it's really difficult. And normally in the industry, we don't actually care much about what is the maximum, but we care about the minimum. So, and testing the maximum is always difficult because you need a lot of concentration. Sometimes it will go that you will never get a time where it will drop. So normally we focus on the minimum explosive concentration. And normal tests are being done using the 20-liter sphere using 2.5 kg igniter. The same way you disperse the dust into the dispersion chamber, then actually with the pressure of with enough air of 21 bar, you're able to disperse into the chamber with the help of ignition source. Automatically, you're going to get ignition. If the material is below the minimum explosive concentration, you are not supposed to see any ignition. So this was a diagram which was actually developed by DeLong in 1984 by tests that they performed. And this is how the minimum explosive concentration test goes. So you can see here at the bottom here where we have the last. So this is the minimum explosive concentration. Normally you have the pressure which is able to indicate whether it's ignition or no ignition, and you have the concentration. You can see around the lowest limit, you can see we have the last ignition. And below that ignition, you are not supposed to see any kind of combustion. And also you can see the pressure curve. It increases until a specific point where you get the optimal concentration, where you are going to get the most violent explosion. Then it goes down again to the maximum explosive concentration, which is, as I mentioned, is of no use to the various industry because it's really difficult to actually determine. So this is some of the research also done by Eckhoff, and he stipulated that, and I have disagreement to some of them, but it's because we have tested MEC close to I think 15 or something like that. But based on research, they said it ranges between maybe around 30 or something like that to over 10,000. Yes, but normally, there's always the need to test your own material to understand the behavior of your material, and also know the minimum explosive concentration, because it's very, very important in the industry to know what is the concentration at which my material can actually ignite. Also, there's a rule of thumb from ECOF, and last week a client actually contacted us. They said they want to determine under normal atmosphere in the air, just normal building, whether the material or some trace of dust that they cannot even see with their eye, whether it can cause explosion. I said no, because in the normal room where you have some dust that you cannot see your eye, that crowd that you don't see actually cannot cause explosion. But this small dust can accumulate on surface. We can cause a fire hazard and also a secondary explosion hazard. But so there was a rule of thumb from Ekov, and he indicated that in case you have 40 gram per meter cube of a coal, and you have 25 watt of a light bulb and 2 meters distance, you are not able to see through. This is coal, because coal is dust, is dark. But usually the cloud of that's going to cause explosion is something that you can see with your eye. So that is something that needs to be taken into consideration. But trace of dust in the air actually can accumulate on a surface that can actually cause a fire or secondary explosion risk. There's another scenario that normally we or people ignore in the various industry. We call it hybrid mixtures. Hybrid mixture occur when you have two state of material in the same system, whether it's a dust and solvent or dust or gas in the system. And this is something of very, very particular important, because uh, if I have a dust, or normally happens in the pharmaceutical industry a lot, in the pigment, the paint industry, where we add a powder into a reactor containing flammable solvent. In this case, we are not accounting for only the dust, MEC, but we are accounting for the flammability of, excuse me, let me take some water. In this case, you are actually accounting for the explosibility of both mixtures. A typical scenario is what is the data presented in this slide, where we have vitamin with minimum explosive concentration between 70 to 80, and also the minimum ignition energy value soon of 300 to 500, and adding maybe trace of ethanol at below its a lower flammability limit, that's 60% below the flammability limit. And if you know, as we mentioned, at below the flammability limit, we are not supposed to get ignition. So both tests was done under both minimum explosive concentration flammability limit of both ethanol and vitamin. Mixing them, then you can get something called synergenic effect. Then you can see that the minimum explosive concentration drastically reduced from 70 to 30, and also the minimum ignition energy reduced from 300 to 3. So that means we have the addition of ethanol at non-explosive will actually increase the amount of combustible in the system. So that is something very, very important that needs to be addressed. Anytime you are looking at or you are doing hazard assessment, this needs to be actually considered. So how do we actually control combustible dust? So normally it's fuel. And how do we ensure that the dust in the system does not exceed the minimum explosive concentration level there? So number one, we need to actually minimize escape of dust from the process through proper design, operation, and maintenance. This is very, very important to ensure that the dust, if it's a container, it needs to stay there. And the container needs to have appropriate protection, which will jump into that soon. If there's a system where maybe the dust is coming out, you cannot do anything about it. By all means, you're going to get some trace of dust coming out. You cannot contain the dust. Then we need to think of local exhaust ventilation and exhaust system to capture this dust into actual appropriate dust collector, which is actually protected. And also, if in all the first, second, the second, you still have some trace of dust accumulating on equipment, then we need to also establish a PM program where we have to clean the dust on a frequent basis. And also we need to know the MEEC, as I said, which is always needed to know the concentration at which the material can actually ignite. How do we actually clean? Because the dust, because if the dust cannot stay inside the equipment, automatically it will come out and accumulate on something. So the most common and preferred method is using vacuuming, ATEX rated or class 2 rated vacuum cleaners. And I don't work for NFPA, but I see that some of their products are really good. And also you can, after that, you can sweep, you can use water wash down. Water wash down is, you need to be careful. If you are handling combustible metals such as aluminum and other reactive metal, you don't want to use water. Otherwise, it's going to react with the metal to generate hydrogen, which is more easy to ignite than even the dust itself. And sometimes too, in case you have inside the equipment, you try to clean, you try to vacuum, and you still have some trace of dust, then you are allowed to use compressed air. But in this case, there are a lot of guidance that you need to follow to ensure that every combustible material are taken for all the ignition source are actually covered so that you don't actually generate crowd that is actually going to lodge into a specific ignition source and also cause explosion. So those are the concentration aspect of it. What about oxygen? So one thing that usually most companies they do is, now I have my fuel in the system. I can't do anything with it. I can do away with my fuel because that is my main product or my reactant. But I also have a prompt of explosion. There's possibility of getting explosion in my system. So what do I need to consider here? Then my prevention approach that will come to my mind is, can I actually eliminate oxygen? Sometimes people say, okay, let me try to use, we have various bases of safety. The first one is avoidance of a flammable atmosphere, which is either removing oxygen or the fuel. And also the secondary is the ignition source. But to be sincere with you, the reason why the ignition source secondary is you can never eliminate all ignition source. So the primary one is the most important thing if you want to prevent any explosion. Number one is the fuel and the oxygen. And usually, in order to actually use oxygen as the basis of safety through inerting, that means you need to know you are limiting oxygen concentration. Last year, we did a project for a client where they have a 3D printing system, and the 3D print they continue getting fire upon fire, sometimes big flash fire. And so they called us, and I spoke to the client and I explained to the client what is going on. He said, yeah, we are inerting the system with argon and still we are getting fire. Then I said, okay, first of all, do you know you are limiting oxygen concentration? They said no. Okay, can you take samples to the lab for us to test? They brought sample. We tested it and the minimum or the limiting oxygen concentration was 3.5. Then I called the client back. Okay, so how do you set your system to for the argon? What is the oxygen level? They say is 6. That means even though they have a good intention of using oxygen, avoidance of oxygen as the basis of safety, but they are doing the wrong way because they don't know the limiting oxygen concentration. That is very, very important when it comes to prevention of any kind of dust explosion. And so these are some of the data. So this don't take don't use these data, please. But this is just a generic data for some of this material because I expect you to test your own material because there are several factors that actually influence the explosibility of various materials, such as the particle size of the material, such as the moisture content. There are several factors, but this is just a generic data. And because we tested some aluminum, which even was 3.52 or 4. So we need to be careful here. But these are some of the data which are available or just to get some fair idea. And the most common inert that are normally used are maybe nitrogen, carbon dioxide, or argon, which are normally used to actually would move oxygen from the system. And normally, you need to also apply safety factor. And before you do that, you need to consult an expert to understand what is supposed to be my set limit for oxygen in my system. So knowing the LOC, normally safety factor of 2. If it is 5, that means you need to set your system to 3. So that needs to be discussed with an expert like us for us to help you. So the first thing, we have finished with the first session of it, which is avoidance of flammable atmosphere, which is removing the concentration in oxygen. The second aspect here is the secondary basis of safety, which is controlling of ignition. So per research, there have been almost about 13 ignition sources which have been published in the various industry, and you can see the list here. Open flame, but the most common ones in the various industry are frictional heating or spark. And we have self-heating of the material, we have arc from electrical equipment, and electrostatic discharge. These 4 are the most common ones in the various industry. So first thing, we need to jump on one of them, that is avoidance of electrostatics or prevention electrostatic discharge. And in order to do that, you need to know the key parameters associated with electrostatic discharge, that is the minimum ignition energy. Minimum ignition energy is the least amount of spark energy needed to ignite an optimum concentration. The term here is optimum concentration. The point here is below the minimum ignition energy, we are not supposed to actually see ignition, no matter the concentration or the change concentration, that actually you are not supposed to get ignition. So, and there are several parameters that needs to be addressed. The concentration is important. The particles are moisture content, temperature, oxygen content in the air. All of them play important role when determining the MIE. But it's very, very important to know the minimum ignition energy of every power that you handle, so that you can have appropriate measure to prevent electrostatic spark or electrostatic discharge. As I mentioned, don't also take my word for this. This is just a generic data. So these are some of these materials that we handle, and some of the data which has been reported in literature and also in our lab. But please don't use this data. Test your own material, because there are several factors that actually affect this kind of testing. So I expect you to get your own data and don't use literature data. So what is the meaning of the data when it associated with minimum ignition energy? So you can see on the right here, I hope you can see them here. You can see when the minimum ignition energy is greater than 100, that means we will say it's a little bit less sensitive. Greater than 1,000 is less sensitive, but greater than 100, yeah, normally you don't need to consider other type of electrostatic ignition, such as discharge from personnel. That is very, very common when handling flammable atmosphere. But when it comes to between, another thing here is human body can generate an energy. Sometimes you notice that you walk on the floor, you touch something, try to move your shirt, you hear a click sound, or you get some shock. These are electrostatic discharge, and this discharge from person can generate an energy up to 30 millijoules, as you can see from the table, so can actually ignite actual dust. So when you have a material where the ignition energy is actually less than 30 millijoules, then you need to think of how you can actually ground an operator by wearing static dissipated shoe and having static dissipative mat, because sometimes I have been to several facilities where they have a good intention, but the applications are actually poor. They have static dissipated tissue, but the floor is insulated floor, or the floor is really dirty. So anytime you try to use using static dissipated tissue, that you need to ensure that the floor is also conductive. That is very, very important. And this is something we can help. And we have been to several facilities to actually do electrostatic hazard assessment, and to actually take measurement and also guide the client on how to mitigate any hazard that will arise from electrostatic discharge. And also when it is less than 25, that is very, very concerning. Majority of the dust that is being initiated by electrostatic discharge materials where the minimum ignition energies are usually less than 25. So that is very, very important. So when it goes below, such as 1 to 10 and less than 1, that means you are at the range of gas of vapor range. And uh, we need to take uh, good precaution to mitigate this kind of hazard. So if you have any material where the ignition energy is very low, what I would say here, contact us or contact any expert for them to guide you on how to actually mitigate this kind of hazard. So these are some of the example of processes that can actually generate electrostatic discharge. As I mentioned, working on the floor, removing your overall, sieving, pouring, and grinding, micronizing, and so forth, and also moving metal cut. All these can actually generate electrostatic discharge. And knowing the minimum ignition energy helps you to actually mitigate this kind of hazard, to know what measures are actually needed to mitigate this kind of hazard. How do we actually control electrostatic hazard? The first thing here is bonding and grounding. You need to, because the accumulation, you need to actually ensure you ground the isolated conductive equipment so that you don't generate static discharge. And you can see how the ground here, and there are numbers. If the actual to the ground is supposed to be 0 ohms, and other equipment, bonding of other equipment needs to be less than 10 ohms. And this is something that we can come with our mega ohm meter to assess various facilities on how to mitigate or control electrostatic hazard. Another thing here is flexible hoses, and most companies, I think almost every company I go, I see such kind of flexible hoses. And these flexible hoses actually can, normally you can see something that's the diagram below, we call propagation blast discharge when there's a breakdown voltage. And usually such kind of flexible hose, they have the spiral wires which goes through the to make it to hold the flexible hoses. And if you have a breakthrough voltage, you can have an energy which is propagation blast discharge, which is greater than 1,000 millijoules, and this can ignite almost every dust. So usually, in case you are handling material which is actually combustible, that means you need to ensure that number one, the spiral wires needs to be mounted and grounded, and if the ignition energy is very low, then you need to consider actually having the hose participative hose. So the hose needs to be conductive itself. The internal lining needs to be conductive, and the wires needs to also be bonded and grounded, which is very, very important. What about flexible intermediate containers and what we call FIBC? So at the FIBCs, and sometimes people call it tote, some people call it super sacks. And this is something which is also used to handle or transport various bulk materials. And this is very, very important to know the type. We have 4 types. We have the type A, type B, type C, and type D. And selection of each type for your transportation and storage of your material depends on the minimum ignition energy. For example, if the minimum ignition energy of the material is greater than 1,000, you can use type A, which is something that needs to be, you can use type A. But if the minimum ignition energy of the material is less than, is less than 1,000 to 3, then you need to can use either type B, C, or D. And normally, as you go down, it becomes more expensive. So you need to choose wisely. Number one here is, are you going to test your material to know the actual ignition energy to select the right one, or you just jump to use type D? And sometimes I go to some client and they use type D or type C, which is very expensive. And I ask, did you have the minimum ignition energy, and how did you select it? They just chose it, and it's costing them a lot of money. And after we testing the material, we noticed that's almost about 300 millijoules. Then we tell, no, you can't just go to type B and you should be okay. So always before selecting super sacks, you need to know your ignition energy to know what is the type that I should select. So after the ignition energy, we need to also move to the ignition temperature. We have two type of ignition temperatures. We have the ignition temperature of the dust cloud, and also we have the ignition temperature of a dust layer. The dust cloud is sometimes termed as the auto ignition temperature, and normally this helps us to select various equipment in the various industry, such as maybe dryers, overheating of bearings, and this sometimes can create heat or can create a hot surface that can actually ignite this material. So always is very, very important to know, okay, what is the least temperature that can support combustion of my operation or of my material? What is the least amount of a dust layer where the material can self-ignite by itself? What is the least temperature that actually, if the material suspended in a cloud form, it can actually support flame propagation? So that is very, very important in selecting the various equipment for your operation. And normally, I think I'll jump into that very soon when you are doing area classification, and most of them is basically selection of your equipment is basically based on the various temperature. So if you have heard of T code, I'll come into that very soon. What about the layer? So you can see these are also some of the data. Don't use this data. This is generic data, and you can have to test your own material to determine the explosibility or the minimum ignition temperature of your own material. So the next aspect here is the ignition layer. So ignition layer also determines whether the material I can smother, or maybe it can grow, or the material can actually self-ignite when deposited on a hot surface. So that is very, very important for us to also take into consideration. A typical example is you have maybe a powder on a dryer, or maybe on a furnace, or anything that can actually on a motor in case there's overheating of the system. Is the temperature of generated from the overheating of the system enough to ignite this material? This is something that we need to take into consideration. It's very, very important to know layer of ignition of layer temperature of the material to know, okay, what is my set temperature for my operation? Normally, if you have maybe a mixer or a blender, you can have overcurrent protection, where maybe as soon as the temperature gets to a certain, or maybe you have a specific voltage trip or something like that, it will just shut the whole system. And in this case, you are not going to have overheating of the system. So usually the layer data is usually lower than that of the cloud, and a typical example is what is showing right now. So as I mentioned, selection of equipment, if you have heard something called a T code, the minimum ignition temperature data is always used. So you can see here, if you say T1, you see equipment selection for T1, you need to know the minimum ignition temperature data, or the auto ignition temperature, to say, okay, now I'm going to select a T1 class of material for my operation, or I have to select a T2, T2A, T2B, and you can see, and also we have T3 and up to T6. When you're getting to the T6 area, then it becomes really dangerous. So this data is very, very important for actually doing area classification and also selection of various material. Another aspect is, how do we control maybe frictional heat or impact? Number one is perform regular inspection and maintenance to prevent overheating due to bearing failure and also misalignment or maybe rubbing. That's very, very important. PM is very, very important. And also, in case you receive a material you are going to convert throughout the other process, automatically you need to ensure that you have a magnet or maybe material separator to remove any junk or material from the system that can actually create impact and serve as a source of ignition. And sometimes I think I also investigated an incident in a dust collector where they have central vacuum system and a dust collector, and they use the vacuum system to just take any dust from the floor, and during sucking, they suck something, a metal, which went into the system and serve as a source of ignition. And also, anytime you are doing hot work such as welding, cutting, you need to have a permit to ensure that all the various explosible or materials are actually removed from the system before doing hot work. And I think there also an incident, I think this year, where they have an open system. They were doing cutting and some of the amber from the process flew into the system and actually caused a fire hazard, and it cost the company a lot. So always before we do anything, we need to actually take good precaution before we take any action. The other aspect, which is tertiary basis of safety. So let me start again. We have the primary basis of safety, which is prevention of explosion through removing of the material or staying below the explosive concentration or using oxygen as inert. And the secondary is what eliminating various ignition sources such as electrostatic discharge, and you need to know the MIE or hot surface through friction. You need to know the MIT and the LIT. But what about the tertiary? So this is the cure. So, and initially I made mention of prevention is better than cure. We try to prevent it, but maybe there's still some residual risks or we cannot prevent it. Then you need to think of how we can cure it. Cure means how do we protect ourselves? Yeah, so that when the COVID came, everybody, we couldn't cure it. So we were what? Protecting ourselves by wearing nose masks. The same thing applies to when it comes to dust explosion. The cure is protecting your equipment. In order to protect your equipment, such as explosion relief vent um, or suppression system or containment or isolation, then you need to know the explosion severity data such as the KST and the Pmax. The KST terms come from Stab. That is a German word that means fine powder. Stab, and the KST is being determined by taking the integral version of the pressure. That's the burning velocity. It's pressure, the difference in pressure with time, and you can calculate it by multiplying by the volume of the sphere, exponent 1/3, and this is how we obtain the KST. And so you cannot get the KST direct from testing, but you need to calculate it from the PDT. That's the burning velocity. That's what I would say, the flame travel velocity with time for the test. And also we need to know the maximum pressure, which relates to the energy which is being released after ignition. And so there are classes, or sometimes you hear something called ST1, ST2, ST3, and the ST0. ST0 means the material is not combustible, it's not explosible. So then you forget about it, you think about fire hazard. Then the second aspect is ST1, which is from 0 to 200, which is a weak explosion to moderate explosion. And when we say ST2, which is a strong explosion from 200 to 300, and very, very strong explosion is, or the most violent is the ST3. And normally tests are done either using the cubic meter or the 20-liter sphere and using the 10 kilojoule igniter. And we have the capability to do such tests in the lab here. And this is some of the data. As I said, this is just a generic data. Never use this data, test your own material. And these are some of the data, because some aluminiums could be less than, maybe it could be ST2. We test some aluminum which is in ST1, depending on how the material has actually oxidized. So, and you can see these are some of generic data to actually know the behavior of such materials. So what are the application of the explosion severity test? The first thing is explosion venting. So if I have a baghouse and if I have a baghouse or a dust collector, dust collectors are always prone to explosion. So in this case, no matter how, unless you try to say, okay, I'm going to totally inert the whole system. In this case, you don't need any kind of protection. But if you are not inerting the system, there is, because we have the filters, whether the SOx system or the filter system, and normally when you pause the dust cloud is generally generated in the immediate layer of the filters. And as I mentioned, the secondary basis of safety is ignition source. You can never eliminate all ignition source. So the only thing that is always is the concentration and energetic ignition source. So in this case, every dust collector per the standard needs to be protected. So the protection is having explosion relief, and you can see the shining on the top one, having a low pressure rated aluminum system, and in this case, in case there's explosion, this will open or burst, and the pressure will move from there. Otherwise, you see the picture from the left, you can see that there was a total destruction. So always you need to have explosion relief vent for your operation or your equipment if the equipment is prone to explosion. If the equipment is located outside, then you can use the explosion relief vent. And if the material is toxic, you don't use it. Otherwise, EPA will be on your neck. And if the equipment is located inside close to your wall, you can use it, then you direct the flame outside the building. But if it's inside the building, that means automatically you're still going to get a flame front, and that flame front is actually going to also create a fireball inside the building. So in this case, you need to think of using something called flameless vent. Flameless vent is like a flame arrestor with a lot of meshes in there. And in case explosion happens, it will have to go through those meshes. By the time it gets out, it has quenching, it has actually turned to smoke. I think in Germany, I witnessed such demo where I have to use my hand to be, and I was really afraid. I thought it's going to blow out, I'm going to die. But I used my hand to touch it, and during the explosion, and nothing, nothing happened to me, thank God. But actually, this is for inside equipment, and inside the equipment, if there's explosion, the flame arrestor is going to catch the flame, and you are not going to get any kind of fireball inside the building. And also, this is not recommended for toxic material. For toxic material, you need to consider explosion suppression system, which is usually for indoor equipment. Sometimes I've seen it for the outdoor equipment, which is also good. And so normally in this case, you have a suppressant and I'll jump into a picture where you see how it behaves. And normally it's used for equipment such as reactors, mixers, blenders, pulverizers, and so on. Even sometimes used for dust collectors. And so you can see these pictures, you can see you have the suppressant, which normally they use sodium bicarbonate. And this in the system, we have a pressure sensor or light sensor or temperature sensor in the system, and which is connected to the system, the suppressants. So in case there's any increase in pressure, increase in temperature in the system, it's going to, it's going to trigger. And since it triggers, automatically it's going to release the suppressants and quench the flame. That's very, very important, therefore. And this can be used for indoor buildings. What about explosion containment? And explosion containment is you are building the system to actually withstand explosion pressure. And as I said again, you need the data to do that. You need the explosion maximum pressure to do this. So in this case, you know the Pmax of the value. That means you have to build the excuse me, you need to build the equipment to withstand the maximum pressure. And in this case, all the flanges and associated equipment needs to be that strong to withstand it. And usually, I know it's a hammer mill from Germany. Most of them are really strong to withstand explosion pressure, but you need to still test your material to understand. And usually, this is super expensive. You know, I think that was 2018. I went to Canada to do a DHA there, and they have a sugar silo, and that sugar silo is actually built to withstand up to 10 bar pressure. I said, really? How much? They spend almost $2 million to do that. I said, oh, this was not necessary. Could have done a different way. So, and it's super expensive to do this. So normally we don't normally recommend to client unless it's the super toxic material. I don't want to release it outside. And in this case, yes, try to maintain everything inside so that EPA will actually not be on your neck. So we also have another system called what? Isolation system. So let's assume we have a dust collector or maybe a silo, and there's explosion inside the silo. Already there's a ductwork which is actually connected to the dust collector or the bin on the silo. If explosion happens, the flame will still try to propagate back to the source. So in this case, we need to have a valve, a cut-off valve called isolation valve. And this valve could be either a passive, which it could be a diverter or a passive fluid valve, or maybe a flap valve or choke valve. And this passive device will actually activate and prevent the flame from going to the other surface. We also have an active system. An active system could be a fast-acting valve. You can see from the top image we have a detection system which is interlocked to the valve and the control system and maybe the main equipment. In case there is any increase in pressure or temperature, the detection will detect that, oh, something is going on here. It's going to communicate to the control unit. Then it tells the fast acting valve, please react. Then it will close. The same thing when we are using chemical isolation, and the same thing, we have a detection system, control system, and it tells the suppressant, please release, and it will release and quench any kind of flame. And this is a typical example of the various explosion isolation system. And this is just a summary of the various testing and their meaning. So if you have, and this is used to assess the various risks. And if you have minimum ignition energy greater than 100, usually we say the risk is very low. We have 25 to 100 medium, less than 25 is, yeah, you are in the red zone there. And you can see the ignition temperature above layer and the cloud. You can see here greater than 500, greater than 400 for the layer, and you can see the data here. The KST, if it's less than 50, people say it's low, but for me, I don't care whether it's even 2 or because I look at the Pmax. Even 1 bar pressure can even cause devastation damage to equipment. So we need to consider not the KST alone, but also the Pmax value. And also the fire rate test, if it is 1 and 2, class 1 and 2 is okay. If 2 and 3, need to caution. If it is 5 or 6, then you are heading towards gunpowder side. So you need to be more caution. The same thing applies to onset temperature, moisture, volume resistivity, and so forth. So this is just a summary of all the testing and how you can understand the data based on the various tests that you do. This is just a blast over this usual plan. We do DHAs, and DHA is normally a systematic approach to actually evaluate hazard associated combustible dust handling. And we have a standard NFPA says 52 and also the NFPA says 60 rather than the current one, which actually laid down procedure to actually do DHAs. And I think this discussion is not about DHAs, so I don't want to go details. Actually, we have 3 methods to plant process safety. We can apply all the method. We have the preliminary. This morning, a client contacted me. They are building a new plant and they want us to do a DHA. So that means what? At the design, because they don't have anything. So we do the preliminary dust hazard analysis. That's what I requested for them. And also, we also do race-based, which we have prescriptive-based, but it's code-based. So based on the code, NFPA says 52 or say 54, or maybe now they say 60. And normally the fire marshals, the OSHA, the insurance normally prefer the code base because they want you to meet a specific code. And most of our DHAs are normal prescriptive and hybrid. So I'll jump into hybrid. That's what normally we use. We also have the risk-based, and people consider as what the hazard type, where they have to define the risk, have the risk matrix, know the consequence, know the likelihood. And we have the performance base and prime. We are used to this where we need to do detailed calculation to understand your process. Maybe if you are generating dust, what is the amount of dust which is being generated? Is something we considered. And also we have the hybrid. That's what we use. So normally we do the prescriptive base and also do qualitative risk assessment to indicate based on our experience whether the material, the explosion is high, low, or the risk associated is high, low. Also do DHA relay validation. So with Prime, we do a lot of testing. All the tests I mentioned, go, no go, we have the capability to do it in our lab. And anytime any one of you visit Houston, you are welcome to visit our lab to see our dust explosion testing equipment, and we can also test various flammability limits such as the flash point and auto ignition and boiling point and so forth. We also do volume resistivity testing, such as our electrostatic testing, such as volume, surface, charge decay, breakdown voltage, and so on. And reactive chemical capability, we do the testing and the consulting, and also we have self-heating basket tests for U and DOT compliance sake. Consulting, we do PSMs, we do, and I already mentioned DHAs, electrostatics, area classification. We also do PHAs and hazard loper, both type facility siting, and also do reactive chemical hazard assessment and also consulting. For training, we also do several training. We have in-house, we also do webinar, we also do custom training to meet your specific needs. And our areas include combustible dust to PHAs, DHA, area classification, and reactive chemical testing and so forth. So thank you very much. And these are some of the industries that we handle or we work in. I think we have been to almost these kind of industries. Thank you. And I'm open for any question. So I'm open if you have any question on you can and I think you have our information here. The phone number here is 346-462-3838. If you're outside US, you can add the +1. And the phone number and the email can send it to code@appliedprocesssafety.com if you have any question.
I have a question.
Okay, yes, sir.
Yeah, I think one thing I find is it's some of the biggest challenges is just like identifying and acknowledging combustible dusts. Like some sites have like one obvious, like food processing facilities have one obvious combustible dust that presents an explosion hazard in certain parts of the process. Some processes have a lot of different dusts that could be throughout a facility. And I think one of the biggest challenges I have is getting employers to identify and acknowledge some of the explosion hazards. What I've seen is they can acknowledge that certain dusts have inherently have combustible properties by virtue of their chemistry. But you think of a facility where they have a product in a feed which has a size fraction, and that stuff might escape from the process, and you have dust in the conveyor feed system. You have dust on the floor, you have dust on the rafters of the first floor. You might have 11-story building where you have dust on 11 stories. And so the issue is you can take one sample and the sample might come back with like a non-explosible, that sample. But you might have dust that's very different in different parts of the facility. And so I think one of the challenges, how do you approach, or what guidance do you give to employers to make sure they have not missed dust that could present an explosion risk by virtue of an incorrect approach to sampling or analysis? Do you know what I'm getting at? Because again, if you don't sample your dust collector, you sample your feed, and you don't sample your dust collector, you're going to get very different dust properties. Or if you don't sample the dust that's collecting up in the 11th floor rafters, you might miss out some explosion hazards. So I'm kind of wondering what kind of guidance you give around that, just the sampling to identify and then interpret and apply those findings. That's kind of
So thank you very much. I think this is something very, very common. And this is very, very common to various industries that we have been to, where they handle different kind of materials. And on the floor, as you said, it's a composite material. So depending on the batch that they are running, depends on the kind of material accumulation there. So in this case, at one time, the material is explosible, the other time is not explosible. So normally, this is what normally we actually request here. You have your main feed product. And so what I will do here is I'll consider the feed that you are handling. If maybe you have several materials, then I think my colleague is traveling to Florida today for a similar kind of operation where they make spices, where they handle over hundreds of material, and they don't know how to start, where to start from. So in this case, a hazard assessment needs to be done, and somebody needs to be there and guide the operation on where to actually take the sample. But I think the most important thing here is the majority of the material which is being handled. That is, if you have your main product or main reactant, In this case, you need to test that material. And sometimes you can also do composition analysis to know, okay, what is the percentage of this material inside this dust? Or so that is something that I would say is, if at certain point the material is explosible, certain point is not explosible, then I have to consider my feed to see, okay, what is the most explosive material among the materials that I'm handling there. Or that we have a client that we are doing a test for, where they actually want us to start even mixing for them to see, okay, in case I have this ratio of material and have this ratio, what is going to be the behavior? In case I have this ratio and this ratio. So there's several ways we can help a client. Number one, we can come to the site to actually review the entire process. The second is the client can send us all the type of material they are handling, and they are in quantity, which we can guide them. And also, as you say, we can do some random testing, which could be much expensive. So the feed needs to be tested, number one. The second aspect here is they need to know the batches at which they are operating, the various batches. And also, we need to also have the list of material and the quantity that they are handling. And this could actually help.
Thank you. And on a follow-up question, I guess, is kind of guidance on handling the marginally explosible dusts, the ones that often come back with a weak explosion, that frag is at 40 to 50 range on the standard go-no-go test. I guess my understanding is a lot of those dusts, there's on the standard go-no-go test, the 20-liter, 22-liter sphere, can come back with false, I guess you can get false positives on them. And so I guess it's very tempting for employers to hope that they're not explosible if they get tested under the gold standard 1 meter cube sphere.
Yeah.
But the issue is to rule out all those marginally explosible dusts, in that range, to rule them out as explosible. That's a lot of expensive tests if you want to run them all through the 1 meter cube sphere. So I mean,
Yeah.
do you have any guidance, or how do you handle when you have a lot of materials that fall into that MED range that may not be explosible? I mean, because I don't think it's feasible to test every single one of them with the 1 meter cube sphere. The cost and amount of material is quite onerous. So any guidance on how you manage those MEDs?
Yeah, so yes. So one thing here is the term marginally. I have a problem with that actually. Let me on 2013, I went to Norway for a conference, and they did a live testing there. And the live testing, after they did, they had ignition, and we were almost about 200 people were standing there. They did the explosion, boom, it shook the whole floor. So, and they said, okay, whoever can judge the pressure of the explosion, the person was going to get 200 euros or something like that. Okay. We were saying 10, some of them were saying 8, some of them were saying 5. And they came back, and the pressure recorded was, I think, 1.7 bar. So what we say marginally explosible, I'm not going to consider only the KST. I'll consider also the Pmax to see the Pmax, because Pmax determines the energy which will be released. And also, as you mentioned, what do we do with it? Yes, we have the overdriving effect in the 20-liter sphere based on the 10 kilojoules igniter. The standard ASTM also recommend using the 5 kilojoules, which will be a little bit underdriven compared to the 10 kilojoules. And so when you bring such test to us and we can even go lower energy. We can test 2.5 to see the behavior, which is less sensitive or less energy. So I'm not going to actually based on the KST, saying that the KST is around 45. So the material might not actually ignite in the rare case, but I have to consider the pressure too. And sometimes we can also test in the cubic meter. Is it necessary? So far as the material is explosible, we need to protect it. Unless you do something called performance-based design, the calculations that we can do to determine, okay, what is the concentration in the system? Based on that, what is the ignition source available? And in this case, we can actually rule out one or two things. But if not, the material is explosible, whether it's marginal or marginally, the pressure of 1 bar or 2 bar can cause a devastating destruction to a whole building. So normally this needs to be well discussed and thought of before making a decision on this. And for testing, we can guide you. In case it becomes necessary, we can actually guide you throughout the process, and we can give free on-phone consultation with specific to your needs. We can schedule 1 hour free meeting. Then you can share detail of your situation, and we can see how best we can guide you.
Thank you so much.
Okay. Okay. Yes. Any more question? Okay, so if we don't have much question, thank you very much, everybody, for joining this webinar. You can visit our website. You can contact us. I have my partner, Taylor Zhao, Dr. Zhao, on the call. And if you send us an email, he will also be available as a resource who will be able to assist you. So thank you very much. And we really appreciate you joining this. And I think every month we are going to do a webinar. So if you are interested, you can join all our webinars. Thank you very much.